Hi, welcome back to ABE 474, Indoor Environmental Control. In this section, we're going to be continuing and finishing up our module on psychrometrics, and we're going to take our understanding of the psychrometric properties that we've been discussing, and we're going to start to, if you will, get into the meat of things where we're going to manipulate the properties of the air. There are some rules we have to follow in order to go from one state to another state. So this section will focus on psychrometric processes, and those are, if you will, the roadmap for getting from one state to another. Some are very straightforward and some are a little more complicated. So let's go ahead and get started with them and talk about how do we change the state of air. And so we'll start with the definition. So psychrometric process is a change in the state of moist air caused by adding or removing thermal energy or water vapor. There are two main ways to break down this change in energy, and we're going to need to be familiar with these two terms. The first is called sensible heat. And this is energy stored in a substance. In our case, it's going to be in our moist air. In most of the cases we're going to look at, it's the moist air. And in most of the cases we're going to look at, that it's a change in the energy or energy that's stored in a substance as a result of an increase in its temperature. This can be inverted to also mean that we can decrease the amount of sensible heat by decreasing the temperature. So it goes both ways. And on our psychrometric chart, this is going to be represented by a horizontal line. Okay. And then the other term we want to be familiar with, the other type of energy we're going to talk about, latent heat. This is energy which flows to or from a material without a change in temperature. And on the psychrometric chart, this is represented by a vertical line. So for moist air, when we're talking about latent heat, usually we're talking about a change in moisture content. An example of this would be vaporization. We're going to get into the specific processes for moving from one state to the other, and moving along lines of sensible heat, so horizontal line or a vertical line, you can't necessarily move straight along the line in this direction. In most of our cases, our processes are some combination of sensible and latent heat. So while you may want a certain amount of change in latent heat, you may also have to recognize that it's accompanied by some amount of change in sensible heat, and vice versa. If you want some change in sensible heat, depending on the process you use, it may be accompanied by also a change in latent heat. So that's why I want to introduce those concepts early, and as we talk through the processes, we will talk a little bit about breaking down the process or the change in state into sensible and latent energies. Okay, so let's get started with the first process we're going to look at. And we're going to start with pretty simple processes, and then not necessarily work our way to more complex, but work through the various processes. But the first two are relatively simple ones. So we're going to start with sensible heating and cooling. And some of the characteristics that we're going to take note of when we talk about sensible heating and cooling are that we should maintain constant humidity ratios, meaning that our humidity ratio at our state point 1 should be the same as at our state point 2. And one of the things I like to do always when I'm talking about processes, and also whenever I am working a problem, is to do just a simple sketch of a psychrometric chart. And I would like to see you all doing that as well on your homeworks and in exams and where you need to show your work. It doesn't have to be an elaborate chart, just something that demonstrates that you understand kind of the direction of your move. And so we're going to have a state point 1, and we're going to make that horizontal line, and we're going to move to 2. So when we're doing sensible heating and cooling, there is no latent component. So we do maintain constant moisture within, absolute moisture within our air, and we change the temperature by increasing if we're heating or by decreasing if we're cooling. So we have associated properties with our state points. And we could put all 7 of them up here, but we just put 2 up here because we just need 2 to describe the point, right? So if we want to think about the amount of energy that is exchanged to get from point 1 to point 2, it's related to the mass on a dry air basis multiplied by the change in our enthalpies. If we are working along the opposite direction and we're going from 2 toward 1, we can cool all the way to our saturation line. And if we cool to our saturation line and continue cooling, so then we begin a process called dehumidification. So this happens when we're in our cooling process. And it it begins if we reach the saturation line. All right, so those are the 2 main things I want to introduce as we begin talking about sensible heating and cooling. Now I want to take a look at sensible heating by itself, and then we'll come back and we'll look at sensible cooling by itself. All right, so sensible heating is where we're looking at an increase in temperature. So again, just a quick kind of sketch to remind us what our process looks like. We're going starting at some point, and we're going to move horizontally in order to increase the temperature. And one way that we can achieve sensible heating might be with something like a resistance heater. So if we wanted to represent a resistance heater in a sketch, we could show this is our duct. that our air is flowing through. We have some air coming in and some air going out, and this is a continuous duct, but we're just showing a section of it. And somewhere within that we have a heating element that is supplying some amount of sensible energy or sensible heating. We have some mass of air going in. The air going in has an enthalpy associated with it and a humidity ratio and all the other properties, but those are the two key ones we need in order to work with sensible heating. And then mass coming out and the properties associated with the air that's coming out. Okay. If we want to then calculate the amount of sensible heating required to get from one point to another, we can do a balance on our example. So the mass times the enthalpy plus the amount that's supplied, so this is what's going in, is equal to what's coming out. And then if we want to solve it for the amount of sensible energy needed, then we just need to rearrange this equation. The same amount mass of air going in is what's coming out because we haven't generated any or spent any, so we can just shorten that to the mass of air times the change in the enthalpies, and that's the equation that we showed up above. But now we're going to expand it out a little bit, just to manipulate around it, just as an example how we can manipulate this now that we have a specific example we're looking at. Okay. Bear with me just a minute while I work through the equations, and we'll go back and take a look at it. Okay. So again, if you recall from your thermodynamics in chemistry, then you might recall MCP delta P is MCP delta T is a representation of energy. So we can look at it as a difference in enthalpies, or we can expand the equation out and have, oh, and I left out my mass here. There should be a mass of air there. Mass of air multiplied by your change in enthalpies is the same as your mass of air times your C sub P times your change in temperature. And in this case, your C sub P is a combination of the C sub P in the air plus your humidity ratio times your C sub P of your water vapor. And that combined C sub P specific heat is 2.45 BTU per pound dry air degrees Fahrenheit. And so what was happening over here as we were breaking it out is that we have a combination of the enthalpy associated with the air and the enthalpy associated with the vapor in the air. And the same thing, the enthalpy associated with the air and the enthalpy associated with the vapor in the air. And then if we want to look at the mass of air times the enthalpy associated with the air, and this is the mass of air times the specific heat of the air and the vapor times the change in temperature. So this equation, which is one of our master equations that we saw up ahead, is equivalent to this equation. So So let's look at an example of using sensible heating. This is an example from your text, so I'll try to include most of the steps, but if I don't include everything or every detail about the setup of the problem, you can take a look back in your book. Your book is notorious for skipping lots and lots of details, so hopefully I'll fill some of them in. So this is your HVAC 3.4. And I've made a few minor changes on this one. Just make a note. In general, when I present the examples from the book, they'll be straight from the book, and I'll add a few details in between, but on this one I've made just a few slight changes to. Okay, so in this case we're going to be given, we have some airstream that's coming in. We have 1500 CFM of air coming in, that's cubic feet per minute coming in, that's a volume, at 60 degrees Fahrenheit, 90% relative humidity. And the third property we're going to need on that is the density, so it's 13.31 cubic feet per pound of dry air. And then we know that we want our air to leave at 120 degrees Fahrenheit. And we have been asked to determine how much sensible heat we need to supply, as well as to tell us what's the volumetric flow rate of the air coming out. Okay, so like I said, I almost always start with a little sketch of my process. And again, you don't need a psychrometric chart just to sketch it. You need it if you want to pull some of the properties off of the chart, but just to understand and demonstrate that you understand your the process you're working with, you can sketch that on just a basic stick figure of psychrometric charts, if you will. Alright, so we're going from 60 degrees Fahrenheit to 120 degrees Fahrenheit using sensible heating, so we move along that horizontal line. And then let's see, the next thing we want to do is solve for our mass of air, and the mass of air we're working with is equal to the volumetric flow rate divided by our volume of our specific volume of our air, which is the inverse of our density. And we know that we have 1500 CFM, and we already looked up ahead of time 13.31 cubic feet per pound of dry air, which gives us, well, we need to do a conversion in here. 60 minutes per hour. Go. Yes, okay. That gives us 6,752 pounds of dry air per hour. Okay. We don't have to do that conversion in there. I'm just showing you another option for working the problem. Okay. And then the next thing we want to do is look at the volumetric flow rate leaving. So we're kind of working these in a little opposite order. Volumetric flow rate leaving is just a manipulation of this equation above, but for a state point 2, where we have the mass of air times the specific volume at the second point. Our, let's see, second point is going to be 67, 2 times 14.83 cubic feet per pound of dry air, divided by, again, we can convert back if we want to. And get 1671 cubic feet per minute, or CFM. Okay, this number in this case was just read off of the psychrometric chart. Let's take a look at the psychrometric chart with our properties labeled on here. So in this case, I just went to our starting point and labeled it, and I drew a horizontal line all the way to the end point, and then it can read the properties off from here to get the final state point for that final specific volume. Okay. All right, which was the 14.83. And then if we want to calculate the amount of energy required, the amount of sensible heating required, we can use our mCCP delta T, or if we wanted to, we could look up the enthalpies for our state points and use that equation. And for the sake of time, I won't plug all the numbers in for that one, but you should end up with 99,400 BTUs per hour. So it's important to also kind of start to think now about, as we talk about the energy required, this is the amount of energy required to go from state point 1 to state point 2. In practicality, when you use a piece of equipment to get from that, there's also an efficiency on that piece of equipment. So this is the amount of actual energy required just for the process change, but when you apply a piece of equipment, you have to consider the efficiency of that piece of equipment. So the actual amount of energy needed is going to be greater than this, because some of the energy is lost due to the inefficiency of the equipment that's used. So as we're talking about psychrometrics, we're only going to look at the amount of energy for the state change, for the process change. But as we move through the semester, you may see questions about, you have a piece of equipment that's 80% efficient or 90% efficient, and you would be expected to be able to factor that in. So by the time we get to the exam, you might see that show up, that I ask you a question about, show me you can do the calculation, and then show me that you understand that that's not necessarily the exact amount of energy you need, that you probably need more energy than that. And that kind of factors into properly designing, properly selecting, and properly operating equipment in order to be more energy efficient. Okay, so let's move from sensible heating and go on to sensible cooling. It's going to look very, very similar, but there are a few nuances with it that I want to point out. So sensible cooling looks very much the same as sensible heating, except we start at a point and we move the opposite direction, so we're cooling. And with sensible cooling, you have the potential to hit essentially a stopping point, or it's more or less a changing point. So if you hit, if you cool all the way to 100% relative humidity, that's the saturation line, and you can't continue cooling horizontally beyond that. You start to move down the saturation line. And as you move down the saturation line, you are removing moisture. So the moisture contained in your air does begin to change if you hit saturation, and that begins a dehumidification process. When we sketch what this process looks like in terms of having a duct and what kind of little symbols we use to denote that we're doing sensible cooling, we have kind of a duct with air going in and air coming out at a different state. So a 1, so it's very much the same as our sensible heating process. Some mass coming out. Okay, and then in this case we draw typically some sort of a coil. This represents a heat exchanger, a cooling coil that is removing energy. Okay, and in this case, as long as you don't go to saturation, you're not removing any mass. But if you do reach saturation and you begin to dehumidify, then some amount of moisture is removed, and so you need to represent that being removed as well. So let's look at an example of sensible cooling. In this case, we're going to have 2,000 CFM of air at 95 degrees Fahrenheit and 20% relative humidity as our starting point. If we want, we can look it up and see that the volume of our air is 14.14 cubic feet per pound of dry air. And the enthalpy of that is 30.9 BTUs per pound of dry air. And we want to cool it to 65 degrees Fahrenheit. And if we look that up on the psychrometric chart, or we could use a psychrometric calculator, we would find that the enthalpy is 23.4 BTUs per pound of dry air. So that's our given. We are asked to solve for the amount of sensible energy required to go from state point 1 to state point 2. And our solution is going to look kind of similar to the process, the approach that we used in our sensible heating example. And we can use, again, either of our equations. And in this case, we now have our mass of air, and we've already solved for the second and the first enthalpies, so we should plug in those numbers, and we'll end up with, again, a negative number if we keep it I2 minus I1 because we cooled. So you just need to recognize when you get the sign whether it makes sense or not. And in this case, we are going to need to remove 63.65 BTUs per hour of sensible energy in order to maintain this cooling from 90 degrees Fahrenheit to 65 degrees Fahrenheit for a flow rate of 2000 CFM. One additional, well, first, before we move on, let's take a look at that on the psychrometric chart. So same thing again, find the 95 degrees, go up to 20%, draw a horizontal line to get to your endpoint at 65 degrees Fahrenheit, and from there you can read the properties that you need. And also, once you get a second point, you can use a calculator to get the rest of them. So you can read them off the chart, or you can use a calculator. So one note about cooling. This is kind of a terminology, vocabulary kind of thing. So when we're talking about cooling, you might hear the term tons of cooling. 1 ton of cooling is 12,000 BTUs per hour. And this unit originated because this is the amount of cooling capacity of 1 ton of ice. And I'll try to throw these little pieces of information in where I'm aware of them and when I remember, because while we have these very strange units in the English system, they're usually based on something practical from the history of our evolution of our equipment. And in this case, our original HVAC systems operated with ice. And so this made sense as a measure of cooling capacity for the unit, the cooling unit that we were installing in order to understand how to size it. So when we hear 1 ton of cooling, for calculation purposes, it's the equivalent of 12,000 BTU per hour. And this is still the most common way that we look at sizing and discussing cooling capacities. So you might hear a 1 ton cooler or a 2 ton cooler, and that's the amount of energy that it can remove from the airstream. So that's all for sensible heating and cooling, and now we're going to move on to this section of AB 474 on psychrometric processes is going to be broken into several subsections. The first one that we just completed was sensible heating and sensible cooling. The following sections will be on sensible cooling with dehumidification and heating with humidification and adiabatic mixing, and the last one will be evaporative cooling. So they'll be broken up like that, and stay tuned to watch them all.